Okay, welcome back. In the previous video, we talked about inequalities and we talked about various aspects, and we completed up to here. We defined the absolute value, and then we established the standard property of the absolute value. And let's use either this or that to prove this multiplicativity and then the triangle inequality. Our textbook author decided to use this one to prove both. Personally, I would much prefer to use this one, even though it doesn't look pretty. It's more straightforward that way. Case 1, case 2, case 3, case 4. Case 1, when a and b are both positive, in which case absolute value is the same as just a real number. So ab equals to ab, no absolute value, just trivial. When a and b are both negative, and a is positive, b is negative, a is negative, b is positive, we consider all those four cases and then just prove those by brute force. It works out. Kind of tedious and rather ugly, but it works out, and straightforward too. But our textbook author decided to use this one, and here is a proof which is rather elegant, but not completely perfect. The red equality is a little bit problematic at this moment. Of course, we can make it perfect by proving one additional lemma, but that is a problem. That's a problem I have. If you prove something and leave something out to students all the time, then that could be a bit cumbersome for students to read. But on the other side, on the other hand, it can force students to study, so I cannot really argue against this textbook author because he has his points too. Anyway, let's come back to this. What do you mean by absolute value of AB? By definition, is square root of AB squared. Now let's change the order of multiplication. Instead of AB times another AB, we can multiply AA and then BB. Consequently, we have square root of A squared times B squared. Now, can we decompose this into square root of A squared times square root of B squared? The answer is yes, of course, but you have to prove it. Once you prove it, then we have the final expression like that. In short, square root of xy is equal to square root of x times square root of y if x and y are both non-negative. Well, that's a question, and the answer is of course true, yes, but you have to prove it. How are you going to prove it? Well, using the idea of square root, yeah, you can prove it by squaring both sides and then taking care of the sign. Yes, you can do that, but it's not difficult, but you have to do it to make this proof perfect. But then again, it leaves something to think about to all students, and diligent students will actually sit down and do those, so it works out fine too. Okay, let's go over to the next statement here, triangle inequality. And this is called a triangle inequality because in higher dimension, the left-hand side, a plus b, absolute value of a plus b corresponds to the straight ahead distance, and then absolute value of a plus the absolute value of b is triangular distance, one way and then turn and then the other way. And straight ahead distance is always shorter than or at most equal to triangular distance, stopping one place and then getting the next. But in one dimension, in just R, set of real numbers, that kind of geometric expression doesn't make sense, but we still use the name triangle inequality. How do we prove it? Again, we can prove it by brute force technique. 4 cases where a and b are both positive, where we have a plus b equals to a plus b, just equality. When a and b are both negative, we have negative of a plus b equals to negative a minus b, where everything is negative. And then one is positive and one is negative. A is positive, b is negative, and a is negative, b is positive. In that case, this left-hand side we have some cancellation. So we have strictly less than the right hand side. We can actually prove all those case by case, brute force. And I would have preferred to do that, as a matter of fact, because it's easier and straightforward that way, but our textbook author decided to do it this way. First, we begin with a complete square formula. A plus b total quantity squared is a squared plus 2ab plus b squared. And then let's make this observation. A is less than or equal to absolute value of A, right? Yes, that's true. Because, let's see. This absolute value of A is either equal to A or greater than or equal to A, where A is negative and this one is positive, or both positive. Same for B and absolute value of B. Absolute value of B, that's bigger. So what we get, this times that is less than that times that. Well, we can actually prove it. As a matter of fact, our textbook author leaves this one as a homework problem somewhere, back in the exercise set. I'm talking about something like this, as a matter of fact. Oops. Or shall I call it proposition? It's too simple. And I forgot the page number. A times B is less than or equals to absolute value of A times absolute of B. Well, the reason is this. AB being either negative or, in case of positive, is the same as the absolute value. So this is less than or equal to absolute value of AB. And absolute value of AB is equal to absolute value of A times absolute value of B, as a matter of fact. I ended up giving away an answer key of a homework problem. Well, okay. Alright, I kind of regret it, but well, here we go. So it turns out that AB is always less than or equal to absolute value of A times absolute value of B, and that's what we are using here. This one is less than or equal to that one, always. Consequently, this second line is bigger. And then let's make one further observation. Actually, this should be an equality, excuse me. This A squared is the same as absolute value of A squared. This B squared is the same as absolute value of B squared, because squaring makes everything positive. And consequently, this third line is equal to, this should have an equality too, this complete square of the absolute value of A plus absolute value of B to the quantity squared. So what we have, this expression is greater than or equal to that expression because of this step right here. And if we take the absolute value, if you take the square root of both sides, excuse me, then square root of left hand side is absolute value of A plus B, and the square root of right hand side is this absolute value, because square and square roots cancel each other except for possibly sign, and the right hand side is positive. So here goes the proof, and there's just a little bit of gap where our textbook author left as homework problem. We take care of that one too. This AB is less than or equal to this absolute value of A times absolute value of B. Okay. Or maybe I should have kept this one as one of those example. Like that, and then A times B is less than or equal to, there you go, absolute value of A times absolute value of B. There's no need for this dot here because this is multiplication. And As a matter of fact, we proved it already. Okay, so everything is complete. Now, do we have some time to go over to some example problems? Well, this is too simple for our class time, so let's just leave it as is. By the way, they appear in our textbook. What page is it? Yes, refer to page 13 of our textbook for this example 1.10. Let's go over to this exercise set, and this one I think is a little bit worthy of our class time because we have some proof problems. First, when x and y are both positive, when x is less than y, then x squared is less than y squared. Why is that? By the way, we can prove under the same circumstance square root of x is less than square root of y as well, but that's going to be a bit harder to prove, so I'm going to leave that as a non-required homework problem, and let's just go back to this. How do we do that? From here, we'll just multiply us selected positive numbers. If I multiply by x, then we have x squared. If I multiply by y, then we have y squared. So those are the best choices, and indeed we use those. Start from here and then multiply x to both sides. What do you get? X times x is less than x times y. Left hand side, x times x is just x squared, so we have this. Now from the original, we multiply y to both sides, and we have x times y is less than y times y, which is y squared. So what do we have? X squared is less than this. Y squared is greater than the same thing. So what do we have? We have this transitivity. X squared is less than x times y, and that's less than y squared. Consequently, x squared is less than y squared. Next, we have this. This quantity, square root of xy, is called a geometric mean. X plus y over 2 is called the arithmetic mean. So this one is asking us to prove that geometric mean is always less than or equal to the arithmetic mean. How do we prove it? Well, we're going to use this kind of idea. X plus y over 2 minus square root of x times y, and see this if this is greater than 0 or not. That's what we are going to prove. If that's true, then certainly this will be true, because all you have to do is flip this square root of xy to the other side. Or equivalently multiply everything by 2. You can ask this question too. If this is true, then of course that one is true. Alright, here's the proof. Start from that quantity, x plus y minus square root of x times square root of y, yes, the same quantity we discussed, and manipulate like this as a complete square, because x is equal to square root of x squared, and y is equal to square root of y squared. And consequently, we have a complete square in the right hand side. So we have square root of x minus square root of y, total quantity squared. And this is squared, so it's always non-negative, as we see over here. Equality takes place if and only if we have 0 inside, which means square root of x and square root of y are the same. In other words, x and y are the same. Otherwise, we have strict inequality. Flipping this quantity to the other side, we have this, and then dividing everything by 2, we get what we want. Final problem, how about this one? They're all positive, and a is less than b and c is less than d, then ac is less than bd. Well, again, we'll have to multiply a certain number here and a certain number there, but what numbers? We have to select something clever. Well, here it is. To the first inequality, a is less than b, we multiply by c, so ac is less than bc. To the second inequality, c is less than d, we multiply by b, so we have this. So what do we get? This bc is common, that goes in the middle, so ac is less than bc, and in turn bc is less than bd, consequently ac is less than bd by the transitivity. That's how we can prove this. And that concludes our review on inequalities.